This is Jack Jackson. This is the first of a series of videos where we're going to be talking about complex numbers. So let's start back at the very beginning and think about numbers a little bit. So the most basic numbers are the natural numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. They go on forever. The lowest one is 1. And these are the counting numbers, the numbers that we use to count with. The most primitive cultures all had some sort of natural numbers, some names for these. So these came out very early in the history of mankind. When you have natural numbers, one of the things that you may want to do, if you're using these to count things, what if you have two groups of things and you want to count the total number? Well, that leads us to an operation called addition, our most basic operation where we count the total number from two groups put together. Now, if we want to repeatedly do addition, adding the same thing over and over again, that leads us to the operation of multiplication. So we're repeatedly adding the same thing over and over again. For example, 2 times 3 means 3 plus 3. 3 times 2 means 2 plus 2 plus 2. So the first number tells you how many groups that you have, and the second number is the number per group. Or the first number tells you how many things that you're adding together, and the second number is telling you what those things are. In a similar way, we can repeatedly do multiplication, and this is exponents. So exponents are just sometimes called powers. And that's repeated multiplication. For example, 2 to the third power means 2 times 2 times 2, and 3 to the second power means 3 times 3. So it's repeated multiplication. So as long as the first number is a natural number, multiplication can be thought of as repeated addition. And as long as the power is a natural number, we can think of exponents as repeated multiplication. Now, we're going to expand not only our idea of number, but our idea of what's meant by these operations as we go along. And really the thing that comes to mind is, once you've got these basic operations here, which are defined for all natural numbers, we want to reverse those. Okay, so for example, if we want to reverse addition, we want to be able to solve missing add-in problems. Like we want to solve an equation x plus 3 equals 1. But we know that there's no solution to that in the natural numbers. But, we ought to have a solution to that. It seems like we should be able to do that. So to do that, it leads us to the operation of subtraction. But that requires us to expand our number system to the integers. So there's a step along the way where we also throw in 0, which is a whole 0 plus the natural numbers, or 0 union the natural numbers is the whole numbers. And then we throw in the opposites of all the natural numbers as well, and we have the integers. So they include 0, positive and negative 1, positive and negative 2, and so forth. Sometimes we'll use a symbol Z for these, for the integers, and so we'll see. We'll use this kind of a number like this for the natural numbers, which are a subset of the whole numbers, which are a subset of the integers. Okay. The integers are going to be a subset of the rational numbers, which we use a Q, and then and those are a subset of the real numbers, which are going to be a subset of the complex numbers. So we're eventually working our way to the complex number system, and those are kind of the symbols as you write them by hand. Okay, so we've made it as far as the integers now, so we can add and subtract two integers. Now, we can put these together. Now, what if we want to reverse multiplication? So if we want to solve an equation like 3 times x equals 4, we need to be able to divide, do the inverse operation of addition, which is called division, and 3x times 4 has no solution in the natural numbers or even in the integers, so we have to go out a little further. And when we go out further, we go out to the rational numbers. So we need fractions for this. So the rational numbers are numbers of the form p over q, fractions, where the top and bottom of the fraction are integers, but the denominator is not 0. This turns out to be the same thing as repeating decimals or terminating decimals. So numbers that are in decimal form, that where the form either repeats or terminates. So we can think of division as repeated subtraction. We can also think of it as multiplying by the multiplicative inverse, or undoing multiplication. We use that for solving missing factor problems, and that requires us to go out to the rational number system. The rational numbers are quotients of integers, so we use a Q for those, reserving the letter R for reals. And by the way, the letter Z for the integers is for the word Zahlen, which is German for integers. This is Q for quotient, but that's the rational numbers, and that is the integers. Okay, so moving right along, what if we want to go out and go further than that? So with as far as we've gone with the rational numbers, we can add, subtract, multiply, and divide any rational number, and everything works out just fine for those 4 operations with rationals, except you cannot divide by 0. And other than that, with that one exception, we're pretty good on all of these things. But if we want to undo exponents, for example, we want to solve equations that have exponents in them, like x squared equals 3 or x squared plus 1 equals 0. Those are equations that just have natural numbers in the equation, but the solutions require us to go out further. So x squared equals 3 requires us to go out to the real numbers. So the real numbers include the earlier ones. So notice that natural numbers, whole numbers include the natural numbers, integers include all whole numbers, including naturals. Rational numbers include integers, whole numbers, and natural numbers. And real numbers include rational numbers, which means they also include integers, whole numbers, and natural numbers. But real numbers are all decimal numbers, repeating, terminating, or non-repeating, non-terminating decimals, and they correspond to the points on a solid number line. They're actually defined to be limits of sequences of rational numbers, but this gets us, these often come from things like radicals. So a square root of 3, for example, or negative square root of 3 would be the two solutions to this equation, x squared equals 3, and those are real numbers. But this one here, x squared plus 1 equals 0, says x squared equals negative 1. And we know if we square any real number, we either get a positive number or 0, but never a negative. And so this allows us to go out to a bigger system. And complex numbers include real numbers, and so that includes all these others. But they're the form a plus bi, where a and b are real numbers, let's see if I can get my keyboard working here. And I is the principal square root of negative 1. And these are going to correspond to points in a plane, as we'll see in a minute. So they also include, they have this form a plus bi, where a and b are real numbers. Now, notice if the b is 0, then you just get a real number. So the real numbers are included in the complex numbers. And then they also, if the a is 0 and the b is not 0, you get a form bi, where b is a non-zero real number. That's called an imaginary number. But notice that complex numbers, there are many of them that are not real, neither real nor imaginary. So 3i is imaginary, 4 is real. These are both complex, but 3 plus 2i is complex but not real. So these are real. This is imaginary. 3 plus 2i is neither real nor imaginary, but is complex. Unfortunately, I've seen some books will call anything that has a non-zero imaginary part here to be to be an imaginary number, but this part's the imaginary number. That's a real number, but when you put it together as a single number, that is a non-real, non-imaginary number. So this is the complex number system, and the complex number system is our basic number system. It's very useful. So you can add, subtract, multiply, divide, exponents, and radicals pretty much at will within the complex number system, and you can solve any polynomial equation in the complex number system. So it's a very nice number system. It's very complete in some ways. So we're going to be working with these complex systems, and in the following videos we're going to talk about different forms of writing the complex number system, how we can visualize them on a coordinate system, and then how we can do operations with these numbers.